This website makes learning so easy. I found all my resources here.
Like what you share.
Okay, let's dive into this. Today, we're taking on a topic that honestly sounds like pure magic, but is actually grounded in some of the absolute most rigorous physics of our time. We are talking about quantum teleportation. Our goal for this explainer is simple, but kind of ambitious. We're going to separate quantum reality from science fiction and figure out exactly how scientists are transmitting information across space right this very second.
So here's our roadmap. We'll kick things off with sci-fi versus quantum reality, move into the basics, break down the protocol and math, look at some wild experimental records, and finally explore logic gate teleportation.
All right, Section 1, Sci-Fi versus Quantum Reality. It is the question literally everyone asks when they hear the word teleportation, right? Can we teleport like in Star Trek? You know, step onto a pad, completely dematerialize, and suddenly reappear on the surface of some distant alien planet? Well, as much as I would absolutely love to say yes, the reality of physics has a slightly different answer for us. Here's the stark difference. In science fiction, teleportation is all about transferring physical matter, actual atoms and objects, from one location to the next. But quantum teleportation? It's transferring only quantum information. There's no physical transfer of matter or energy happening at all. Now, what's really interesting about this is that the sender doesn't even need to know the specific quantum state they're transferring. And because this whole process requires sending traditional, classical information right alongside the quantum stuff, it can never, ever happen faster than the speed of light. Moving on to Section 2, the basics. Let's do a quick, non-technical summary. Everything starts right here, with the absolute simplest unit of quantum information, the qubit. If you think about a classic computational bit, like the ones processing this explainer on your phone or computer right now, it acts very rigidly as either a 0 or a 1. A qubit, however, is a whole different beast. It has this incredible dual nature, where it can behave as a combination of both a 0 and a 1, at least until the computation is entirely over. This two-state system is the core carrier of the information we actually want to teleport. Next up, we need the magic ingredient, which is quantum entanglement. This is what happens when you place two or more separate particles into a single shared quantum state. When they're entangled like this, measuring the state of one particle instantly gives you information about the other, no matter how far apart they are in the universe. It's a completely spooky phenomenon, famously known as the EPR paradox. It seemingly defies special relativity because it feels like this instantaneous effect across space-time. But don't worry, Einstein's speed limit is completely safe. Since we can't use this correlation to transmit usable data faster than light, it perfectly respects the laws of physics. So the crucial point is, what do we actually need to make this teleportation happen? Well, we need a sender, traditionally named Alice, and a receiver named Bob. We obviously need the information itself, our qubit, and we need channels connecting Alice and Bob. You absolutely must have both a traditional, slower channel sending classical bits and a quantum channel, utilizing that entangled state we just talked about. If you're missing either one, the whole shebang fails. Okay, Section 3, the protocol and formal presentation. Let's zoom in on the actual mechanics. Here is the step-by-step breakdown of how Alice actually sends her data over to Bob. Step 1. An entangled bell state is generated, with one half going to Alice and the other half going to Bob. Step 2. Alice takes the specific qubit she wants to teleport and performs a joint measurement, called a bell measurement, on it alongside her half of the entangled pair. Step 3. This measurement gives her one of 4 possible outcomes, which she rapidly encodes into 2 normal classical bits and fires off to Bob over a standard network, Finally, step 4. Bob receives those 2 bits. They basically act as an instruction manual, telling him exactly how to modify his half of the entangled pair. Once he makes that adjustment, boom, his qubit perfectly matches Alice's original quantum state. Now, don't let the formal bracket math intimidate you here. It's really just a formalized way of writing down exactly what we just walked through. The top line shows the general state Alice wants to teleport, using alpha and beta to represent that superposition of 0 and 1. The middle line represents the quantum circuit itself. She's using a C0 gate followed by a Hadamard operation. And this brilliantly illustrates how Alice's physical operations literally shift the entanglement away from Bob's particle and onto her own 2 particles. This mathematical change of basis is exactly what allows Bob, shown on the bottom line, to recreate the exact desired state on his end once those classical bits arrive. Now, you might be wondering, wait, did Alice just copy her data? Actually, no. The strict laws of quantum mechanics absolutely forbid perfect copying. It's a rule known as the no-cloning theorem. Because Alice making a measurement forces the state to collapse, her original qubit is utterly destroyed as it gets tangled up into the new state. Teleportation does not copy the information. It dismantles it in one location only to recreate it flawlessly in another. All right, Section 4, Experimental Results and Records. Let's see this in the real world. The timeline of progress here is just wild. The initial theoretical proposal was only published in 1993, and by 1997, 2 research groups led by Sandu Popescu and Anton Zeilinger achieved the very first experimental physical realizations. Let's see how this builds because it escalates fast. In 2004, researchers ran an optical fiber wire through a public sewer system underneath the Danube River in Vienna, proving this tech works outside a pristine controlled lab. By 2012, Zeilinger's group was beaming quantum states 144 kilometers through the open air between the Canary Islands. And then, in 2017, Jean-Wei Pan's team shattered all records by teleporting quantum information 1,400 kilometers from the ground straight up to the Messias satellite in orbit, literally from a damp sewer wire to a satellite in space in just over a decade. And the advancements absolutely have not stopped. In fact, if we look at some incredibly recent developments, in April 2025, researchers at the University of Illinois Urbana-Champaign announced a massive breakthrough. They utilized a highly advanced nanophotonic indium gallium phosphide platform to perform nonlinear sum-frequency generation, or SFG. I know that's a mouthful, but basically, this specialized platform successfully mitigated multiphoton noise, which has traditionally been a huge hurdle in quantum communication. What makes that 2025 breakthrough so spectacular is the fidelity rate. The University of Illinois' team achieved a teleportation fidelity of 94%. This means the quantum information arrived with just staggering accuracy and quality, remaining incredibly faithful to its original state, despite the insanely complex transfer process. But wait, it gets even better. By mitigating that multi-photon noise with their new platform, they didn't just improve the fidelity, they boosted the overall teleportation efficiency by a factor of 10,000 compared to older SFG-based systems. 10,000 times more efficient. This is exactly the kind of exponential leap that takes a technology from a cool laboratory curiosity to a globally scalable infrastructure. It's a real game changer. Which brings us to Section 5, Logic Gate Teleportation and Recent Developments. This right here is the final frontier. It's called Logic Gate Teleportation. Instead of just sending a static piece of data from Alice to Bob, we're now teleporting actual logical operations, like a C0 gate, between logically encoded qubits. It essentially allows for the actual active data processing of quantum information across vast distances. If you want to build a true quantum computer or a global quantum network, this is the foundational building block you absolutely must have. And we are already seeing massive strides here. As highlighted by this quote from a recent paper by Fang and colleagues, scientists have demonstrated that we can now teleport information into systems that are already holding quantum data. By using specialized entangling gates, this means we can perform new calculations based on previously stored information. It's like a giant puzzle coming together, paving the way for vastly improving how we process past calculations in future quantum computers. So think about this journey. We've gone from a theoretical paper in 1993 to bouncing qubits off space satellites to teleporting the very logic gates needed for quantum computation with 94% fidelity. It's mind-blowing. So I want to leave you with this to think about. If we can already perfectly teleport quantum logic and data across global satellite networks today, how quickly will the ultimate unhackable quantum internet reshape our world tomorrow? Thank you so much for joining me for this explainer, and keep questioning the quantum reality around you.
Like what you share.
This website makes learning so easy. I found all my resources here.